Imagine a place where motion itself fades, the edge of absolute zero. Today we explore the physics behind the coldest temperature nature allows. What truly happens at -273.15 Celsius? Temperature is not just a number, it is the average kinetic energy of atoms and molecules. Hotter means faster motion, more vigorous collisions, more energy shared. In solids, vibrations ripple through a lattice. In gases, particles zip freely. A thermometer translates this microscopic motion into a macroscopic reading. So to cool something, we must slow the motion of its particles. Absolute zero is defined as 0 Kelvin, where thermal motion reaches its minimum possible value. As energy is removed, atoms move less, vibrations shrink, collisions dwindle. In the classical picture, you might imagine motion halting entirely at 0 K, but nature is quantum. There is a flaw to how still things can be. Internal energy approaches a minimum, and entropy trends toward a limit. Vibrational quanta, phonons, are frozen out as temperature falls. Gases slow, condense, and quantum statistics begin to dominate. Approaching, yes. Reaching, no. Quantum mechanics imposes the uncertainty principle. We cannot pin down both position and momentum with arbitrary precision. Even at minimum energy, particles retain zero-point motion. Every cooling step leaves a whisper of motion that cannot be removed. This is why absolute zero remains a theoretical limit, not a destination. The Kelvin scale starts at absolute zero, not at water's freezing point. 0 Celsius equals 273.15 Kelvin. Kelvin avoids negative temperatures for typical systems, simplifying thermodynamics. Temperature differences are identical in Kelvin and Celsius. Hence, scientists report temperatures and laws in Kelvin. 17th century pioneers tamed temperature with the first reliable thermometers. Ice and salts pushed systems below freezing. James Dewar's vacuum flask unlocked colder storage. By the late 1800s, air and oxygen were liquefied. In 1908, helium fell to liquid form, opening a new frontier. Cooling power advanced with pumps, shields, and clever thermometry. Each step edged us closer to absolute zero, never quite reaching it. Modern labs use staged cryocoolers and liquid helium to reach microkelvin regimes. Superconducting magnets confine and manipulate ultra-cold atoms. Feedback loops and vacuum chambers keep heat leaks at bay. High vacuum strips away collisions that would warm the sample. State-of-the-art setups cool atomic clouds to billionths of a Kelvin. Layered shields, dilution stages, and filters form a thermal fortress. This is the quietest cold we can craft on Earth. At extreme cold, bosonic atoms collapse into a single quantum state. A Bose-Einstein condensate behaves like one giant matter wave. Phases lock together, granting long-range coherence. Small ripples travel as collective excitations. When released, overlapping waves produce striking interference patterns. Compared to a thermal gas, the condensate is sharply peaked and ordered. This state reveals quantum rules on a human scale. It is quantum matter made visible. Laser cooling uses photons to steal momentum from atoms. Atoms moving toward a tuned beam see it Doppler shifted into resonance. Absorption opposes motion. Random emission averages out. The result is optical molasses, where motion becomes sluggish. A magneto-optical trap adds position-dependent forces to confine atoms. Sub-Doppler techniques push below the Doppler limit. Finally, evaporative cooling skims off hot atoms to reach nanokelvin. Light and magnetism, working in harmony. Superfluids flow without friction, climbing walls and slipping through cracks. Superconductors expel magnetic fields, locking magnets in mid-air. Currents circulate forever, facing no resistance. Rotation breaks into perfectly quantized vortices. Dissipation fades, coherence grows, and the quantum world takes over. Degrees of freedom freeze out as temperature falls. Even electrical noise quiets in the deep cold. Near zero, matter rewrites its own rules. The third law of thermodynamics bars us from reaching absolute zero. It would take infinite steps or infinite time to remove the last energy. Every method leaves a remnant, zero-point energy, stray photons, vibrations. We can asymptotically approach the limit, not cross it. Entropy tends to a constant, yet never reaches the absolute minimum. Nature preserves a flicker of motion at the bottom. Lasers, magnets, dilution. Powerful, but not perfect. The goal is not zero, but control. Quantum computers rely on ultra-cold qubits to reduce noise. Superconductivity enables lossless signals and exquisite sensitivity. Cryoelectronics and quantum networks will knit devices together. In astronomy, cryogenic detectors reveal faint light from the early universe. Ultra-cold sensors promise breakthroughs in materials and medicine. Engineering at these temperatures will become more automated and precise. The closer we get to zero, the more powerful our tools become. Stay curious, explore the quantum cold.